over of various inequalities was to, or is to, upper bound or delta, right? Okay, so mu sub n is our empirical measure. So we wanted to bound the supremal deviation of the true measure from the empirical measure over every element of the R plus class. So for generally x1 through xn are RID random variables taking values in some space x, and A is more generally the collection of subsets of x. With probability of or mu of A being just the probability of any one of a random variables, say x1 being
Yes, before you continue, is it possible that you could move the camera to the other side of it, because it's going to be? I was trying to move along. Yeah, it got in the line all the way.
Okay. Yeah. It might be better
okay?
if we could.
Yes, sure.
Or we could. I could just move it to the center. The thing is, if we do it here, it's almost impossible to see what's on
I moved
okay.
to sit
Okay.
there.
Great.
sorry. So yeah. So what else do we have? And mu sub n. Okay, it's just the relative frequency of the number of points that land in it, or the empirical measure. For any A in script. So that's the more general setting. So we want this to be regardless, to hold regardless of the nature of A itself, right? Like how complicated it is. So regardless of the nature of A, by changing one xi, or our assumption G can change. Well, G can change by at most 1 over n. Okay. So therefore, by bounded difference inequality, we have the following. The probability of event the absolute value of the supremum of mu of A mu NFA minus the expectation of the supreme A, the absolute value of mu NFA, mu of A minus mu NFA, being more than T, this whole event. Next. Is less than or equal to 2 times e to the minus 2t squared divided by the summation as I goes from 1 to n of 1 over n the whole squared. So this is for our difference in quality. Minus 2t squared over n squared, and that's just 2 e to the minus 2nt squared. Okay. And this holds for any n and t greater than 0. And t greater than 0. So what is this? This shows that for any class script A, the maximal deviation of empirical measure mu n from the true measure mu is sharply concentrated around the mean, around its expected value. This was part of a plan, right? So this means delta or G is going to 0 in probability if and only if G goes to 0 almost sure. Only worry about the bounding the expected value. And this was our plan all along. Expected value of the maximal deviation. i.e. the expected value of the supremum over all sets A is script A of mu of A minus mu. Okay. So of course we want to do this in generality. To do this in generality, we need uniform deviation inequalities. Okay. We're going to let the size of A be finite. When this happens, as in our main theorem, choose MDE setting, because there are only k densities. selecting k densities from the set f and I, where 1 is less than or equal to I equal to k, and also they integrate to 1. So for all I, our yacht cost class forming script A. Obtained coming from our ordered pair such FA sets. Right? Well, that's our destination. So if we are in the finite setting, then all we need are lemmas 4 and 6. So now let's look at the next main lemma. This was one of the last ingredients in the bag of all the lemmas. So if my script A is this, now we're getting into another level of nesting. It's the set of all x such that fn I of x is greater than fnj of x, right? So let's start saying earlier, yeah, because this is the k square minus k surface that's with finite k. Then the expectation of delta is going to be the expectation of delta and this is less than or equal to square root of ln 2k squared over 2n. Okay. So let's prove this. So first we note that script A, okay, same script A has at most k square sets, right? Okay, it's actually k square minus k sets. So it has at most k square sets. And then let x of a equal mu of a minus mu sub n of a for each of these sets A. Then for s positive, low small s positive, we have the expectation of e to the s x at a is equal to the expectation of e to the s. You just plug in definition here for mu(n) and xa. Okay, so close that and do that. So we are interested in the expectation of that. So usual 90% of maths is chasing the definitions. So then we have the expectation of e to the s 1 over n summation as I goes from 1 through n of mu of a minus the indicator function. I just move the mu of a inside and nothing's really going on. So next, we just pull the products. So I can just rewrite it like this, and nothing is going on. I already pulled this out. So e to the minus s, and then I have mu of a minus the indicator function of xi over n. Okay. So then this is just because we have the independence x1 to x. We can do this operation. But this is less than or equal to the product as I goes from 1 through n of e to the s squared 1 over n the whole squared over 8. Okay. So this is why our lemma 4. Why? Because since the expectation of the event mu of a minus xi in a over n, this is 0. Okay. And what else do we need? And then mu of a, this just depends on how you see it. Yeah, so mu of a over n less than or equal to mu of a minus the indicator function of xi in a the whole over n and 1 over n. And that's how this gets plugged in. So, let's continue. So note that we also have expectation of okay, so let me do this a little bit more first. So we have this, and let's just do a little more cleaning up. So this will be s squared over 8 and summation of 1 over n squared. That goes from 1 through n. So this will just be e to the s squared 1 over 2 root n squared over 2. Okay. Yeah. So we also have the expectation of e to the s of minus xa, which is less than or equal to e to the s squared of 1 over 2 root n squared over 2. So all of this gives us thus for each a in script a, x of a, which is defined as mu of a minus mu n of a, and expectation of e to the s xa is less than or equal to e to the s squared sigma squared over 2, where sigma is 1 over 2 square root of n. So putting all this together, the expected maximal deviation inequality, we get that the expectation of the maximum over this collection a of mu of a minus mu n of a is equal to the expectation of the maximum and so this thing is less than or equal to 1 over 2 square root of n square root of 2 ln of 2 times the slice of a. And this is less than or equal to 1 over 2 square root of n square root of 2 log n 2k squared, because that's how big our class can be most. And so this gives us square root of ln of 2k squared over 2n. So for the full asymptotic story, I think I need to use the absolute value version of this thing, probably where I'm going wrong. The stuff is leaking out on the other side, right? The way I correctly both the negative.
I think it's fine. It's one. I mean, it is one of these. It should look like this exactly how to justify it. I mean, this.
Yeah, but I don't like that. I should just. I don't know.
Don't worry about this.
Yeah, I won't worry about it. I'll figure it out.
Take it to it at the break.
But yeah,
this is exactly the type of thing you shouldn't try to figure out at the blackboard, because
yeah, true. That's anyway, so that's KP. So now finally from number 9. And taking expectations in theorem 2. We get our full asymptotic story. For MDE. This specific problem. Selecting from a finite set of k densities. So this is corollary 10. So we have that the expectation of the integral of the average value of psi n, which is our MDE and f. So the expected L1 distance of the MDE from the truth is 3 times the minimum, right? This is the part we get from theorem 2. 1 k integral of f n I minus f. So that's the 3 times the best possible thing in your set. Even without knowing anything about what the true f is, right? If this is guaranteed. Plus square root of 8 times the natural logarithm of 2k squared over n. So this is kind of the more basic insight behind these tree-based histograms we built in C++. Okay, this is so non-distributed. So let's get some numbers. What does corollary 10 really mean for us? And we just have to look at this, So if something that I have the natural control over in this sense, as long as my f and i's are approaching f in some clever way, like this distance I control by making sure f and I is a flexible enough family. So as n goes to infinity, so for example, if f and i's are in some finite sequence that approaches any continuous density, then I'm happy, if I have to say continuous. And then here I just have to make sure that k is not completely crazy. It has to you have k squared, but then you have logarithm as well. So let's look at some actual numbers. So we have so the corollary 10 has some applications. In situations where k is allowed to grow with the sample size n, say as k sub n. So we are now subscripting k by n and say as n grows, our k sub n also grows. So the set slowly gets bigger with n. So we want it such that the minimum k sub n of the integral L1 distance. So the best thing goes to 0. So this you do somehow by making sure that this set is dense enough and can get into close to some things where f lives as k sub n goes to infinity. And we also want the other term, right? In the forward. So, and the square root of 8 ln of 2k sub n squared divided by n. This guy is going to 0. So for example, consider for our choice ln of kn, we want this to be less than root n, for example. Right? And so we want k sub n to be less than or equal to exp of n to the whatever. I like this number. Okay, so that's not, well, yeah, it has to grow, sub exponentially in the square root of n. But so concretely, let's look at what this means. Concretely, let's make a little table. This is kind of the first thing we started doing before coding. So what this theory kind of tells us is if I have n, k sub n, let's say this is the flow of e to the n, I'm just going to put 7 over 20. Okay, so that's less than 10 over 20. And then I have, say, the square root of 8 ln of 2 k sub n squared over n. And I have k sub n to be the flow of n to the 5 over 20. So there's a couple different setups. So for this kn, my square root of 8 ln 2 kn squared over n goes like this. So for a sample size of 100, in the case of n, it's 150, and this term is 0.926. The case of n is 23, this term is 0.750. Okay, so let's look at 10 to the 4. So if I have 10,000 samples, this is roughly 8.1 times 10 to the 20. Quite big. And this becomes 0.202. And this one is only 22,026. 0.02. And if I had 1 million points, this is roughly 4.7 times 10 to the 54. This is 0.045. And this is about 5.4 times 10 to the 15. And this is about 0.02. Okay, so that just gives you rough ideas of how, without making any other assumptions except the size of the kns, how do these terms behave? So the real question is, how do we control the first error term 3 times the best possible estimate in your k-ns, right? So we really have to control that by engineering the case elements of k sub n of them as n goes to infinity, that this set will somehow enclose f, right? So there are 4 situations to consider. So,
sorry, super quick question. the K sub n, that is the number of densities we are investigating.
Yeah, that's right. Yeah, exactly. Because we want them to grow with n,
Yeah.
otherwise you can't hunt f, right? But yeah, these are just some numbers to give us an idea of, you know. So there's a big range, right? So how to control first error term? So since we have someone from SCB here, I'll give you my situation 1, 2, 3, and 4 in real world. So situation 1. Situation. So let's write this down explicitly. So this is 3 times the minimum of the best guy, and I, and the stuff we don't know. So how do we control this? So situation 1 is the best if, so for us, like a bank problem, the true unknown f is the density of some features of a particular transaction, right? So this means, say we're looking at, I don't know, we use Swish a lot, so say we're looking at Swish transactions, and if it's Swish transactions, natural features will be a timestamp of the transaction, the user account that the money is going out of, the user account the money is going into, and then, you know, there could be the time at which the user started the account that the money is coming out of and going into. It's already what we have 1, 2, 3, 4. We have 5 random variables. I mean 5 dimensions, for example, right? Some of them are discrete, some of them are continuous. Let's focus on the ones that can take continuous values. Also the amount of the transaction. So in general, you're going to have some underlying density f that is reflecting the true state of safe transactions, you know, not fraud or whatever. Same problem in cybersecurity, right? Except the feature space is much different. Probably do some projections from the network information, from log files or whatever. But in general, that's our unknown. And if we can get the density estimate of the unknown from historical data, we have some handle on how to treat new data that's coming at us, right? Does it look like history or not? That's basically anomaly detection. So in what are the different situations? First of all, this unknown f has in the first situation, it's great because it somehow happens to lie in our set itself. Right? So it's in the set, it's an element of the set of all f and i's. So it's one of these k guys. Start out with. Then the minimum is 0, right? Then this minimum term, right? This is 0. Because we just have the best guy right there. Then this is useful in some situations where you control and play God, right? I don't know. This is useful in, you know, simulation situations, right? Where you. So we do it a lot. So this is our usual debugging tool because these 3 arithmetics are not really easy to debug. So we will usually make sure everything works by producing you know, a very large K, but then we will simulate sample densities, samples from that particular K. Then a lot of the theorem will really wash out very cleanly because this is 0, so then at least we can make sure that it behaves like we expect. So this situation is very rare, right? It's not a real world situation. Okay, so situation 2. So now suppose f is an element of some script f tilde, right? So this is a class. So we're going to call this, this is a class of densities, say totally bounded densities. So what is this? So that is for every epsilon possible, there exists a script G sub epsilon. So this means there exists a script G sub epsilon, which is defined as set of G1, G2 up to G sub n sub epsilon. So this big number, it may depend on epsilon itself. So we have this G's, and these G's are a subset of script f sub epsilon such that script f tilde is itself a subset of the union as I goes from 1 through n sub epsilons of the balls centered around GIs, epsilon balls centered around GIs. So what is this exactly? So this B sub G comma R is simply the set of all densities, say F, such that they are within the R1 ball, such that the integral of so the R1 distance from F to G is less than R. So we can, this just means the set of all densities F that are within a radius R in the L1 distance of the G. So this ball of radius R centered at G is something, right? And this ball, if we take the ball centered at each GI of radius epsilon, we get a whole bunch of balls. And if these balls somehow cover, if I take the union of them, and if they cover all of F tilde, then that's the definition. F tilde is a class of totally bounded densities. So this is situation 2, right? It's well, it's a little more realistic than that one, maybe. Okay.
So just a quick,
very
short remark for those, in case people just haven't seen this type of thing. Yeah, the rate at which n epsilon grows as epsilon becomes small is very closely related to the dimension of the.
Oh yeah, I think that's
space.
That's
so if you have something finite
right.
dimensional, this will come after some normalization converge.
So say that again. Is a dimensional property?
Yes, it's. I mean,
it's the
exactly
complexity property of the class.
Yes, I mean, but these, if you study fractals and these types of things, then basically you define dimension by the rate at which these.
Yeah.
But it might look a bit weird, but if you sort of throw these things around, this is very closely related to dimension of the space.
Yeah, so this is something Luke told me in the same meeting in Singapore.
Okay.
I refused to go to World Congress until this paper is finished. So I've not gone to any World Congress in probably its stats since 2008. Not a good idea for career in this field. But anyway, one other thing that Luke told me is kind of, I didn't really appreciate it when he told me, but I really understood it later. He was saying, because I was talking about how I'm interested in doing density estimation in high dimensions, and then he said, Ross, don't you know some basic fact from, I don't know, 1920s or something. Someone's theorem, he said, well, there's no such thing as dimensions when you do density estimation. Okay? There is just the complexity. So, and I really didn't understand what he was saying at that time, but it really makes a lot of sense because a density in 1D can be so complex that the number of data points you need to approximate it, can be, so, it can be very, very, very high, right? So the point is, it's not really the dimension that the density lives, that's the problem.
But it's the dimension in the sense of degrees of freedom. So the rate at which this increases, you can think of this as a dimension.
Okay, no,
it gives you the number of directions.
So I'm not, let's forget about this totally bounded thing. I'm talking in generality, right? Because I was just, well, anyway, at least in computational stats, applied computational stats, people are, oh, can you do it for 3 dimensions?
Okay.
It's hard in a different way, but you can get densities in 1D that are so complex to chase that you need a lot of data points anyway.
Yes. But if you assume the densities to be very nice, so smooth and something like this,
then
the dimension of the space of densities is related to the dimension of the underlying Euclidean space.
That's right. That's absolutely true. Yeah. So let's do the following. So sorry, I'm not done with this definition yet. So the smallest. So now we go to this Kolmogorov ideas. So the smallest such n sub epsilon.
Okay, no, sorry.
Is this what you're
Yes,
getting
this
at?
is.
Yeah. It's called complexity. It's the complexity in the sense of covering numbers or covering number. Of activity. And then if you look at what is log base 2 of n epsilon, this is called the Kolmogorov entropy. Well, this is our same Kolmogorov probability theory. Of the class. Okay.
I think technically speaking at resolution epsilon or something like this, right?
Yeah. So it's the Kolmogorov entropy of f tilde for resolution epsilon. So is that what they say?
No, I've heard different names for this.
Anyway, we know epsilon is hanging in here. Let's keep all the jargon down minimum. So and then G and then this thing itself, script G epsilon, is the skeleton of activity. Okay, so this log n epsilon thing, base 2 thing, has something to do with computer science. It has something to do with data compression. And intuitively, it's the number of bits because of base 2 to store an integer between 1 and n epsilon. Okay. So that is situation 2.
Can I just draw a very quick picture?
Sure.
Just for those, in case those haven't seen these types of things. So just if you, with these numbers, I think this might be helpful. Sorry for interrupting.
No.
So just if you think about the number of holes, you need to cover something in Euclidean space. So if you just take something that looks like a line, and we cover this with some circles. So here we now need, let's make this a bit shorter, so we need 4 to cover it. So this is at some epsilon. If you now take epsilon half as big, so you make the holes, make these half as big, we will double the number. Yeah, 1, 2, 3, 4. So roughly speaking, if we make it smaller, we will double the number of holes we need to cover it. But if you do this now for a square, to say we needed 4, so now I'm being very sloppy again. Yeah, and you have these. So we will get 16 instead. So yeah, the rate at which, this is what I mean that this is related to the dimension of the space, because since we now have 2 dimensions, the rate at which this increase will be cubed instead.
Okay.
This is why you take the logarithm, because then the exponential factor just jumps out in front, so it becomes sort of a linear. So this is why we get back basically the dimension in the Euclidean.
Let's see. There's
Three, sorry,
yeah.
maybe a stupid question, but in the situation 2, the normal distribution will fit there, right? Because it's unbounded. For instance, I'm just thinking normal density because the tails go on and on.
Yeah, so
Am I understanding it correctly or?
no, I mean, so you can have, you can, let's say, let's make this very parametric, right, just to understand. So let's say one of your, so fn's are, so sigmas, let's say fixed, and your fn1 through k are Gaussians, and they're just Gaussians with mean at whatever, 1, 2, 3, and to k, right, so that's sitting here. And in the first situation, one of your densities is, say, 3. Centered at 3, it's there.
I'm fine.
But in this second case, what we are saying is that I can look at some epsilon balls around these Gaussian densities. So you have to imagine now for a Gaussian density centered at, say, 1. It's fine. It can sit on the real line. But then there are these, imagine tiny little perturbations of the Gaussian that that are, so I don't know. This is gonna get weird. Let's do it. So you have a Gaussian like this, right? This is our, say, the first guy. Now I want to understand what is a ball around this. So now consider another one that's almost the same, but maybe it goes weird like this, maybe, and compensates. It still integrates to 1, right? That's slightly off. It's definitely not this guy. It's definitely not the fn1, but it's like somewhere close to fn1. And then if I look at the L1 distance between those two, let's say it's less than epsilon. So that's just one little.
So it's the L1 distance.
The
ball covers.
Exactly. It's the ball is a set of all densities that are within some radius. So of course it's only as rich as what the skeleton is. So I'm about to write down. I started writing down here. So these are called skeletons. Did I know? Yeah. So anyway, skeleton, right? So what you can reach.
So if you take the Gaussians and you restrict the mean to some bounded set, this should behave like a one-dimensional thing, because basically you just shift the mean. So it looks roughly like, if you're looking at the set of Gaussians within, say, in one dimension within some interval, this is roughly the same as just looking at the interval, because you just have some probability distribution that you shift. Sort of. So it's the number of parameters that you have of the family rather than how the underlying space looks.
So, okay, let me continue with situation 2, because we have 4 situations. Let's try to get them before we come. Okay, so now I want to define my Yaprakos class for this setting, my situation 2. So define the Yaprakos class. Script A sub epsilon as the set of all x, set of all x, such that gi of x is greater than gj of x for each gi and gj in my g epsilon, right? So that's my Yaprakos class. Then with the size of the Yaprakos class clearly bounded by n epsilon squared, right? Because there are only n epsilon elements in g epsilon. So now the minimum distance estimate of the Yaprakos skeleton estimate is this guy. Psi n argmin of gi d epsilon of supremum over A okay. So that's our minimum distance estimate over this class. Nothing's really changed, like I mentioned. So thus, by corollary 10 and the very definition of n sub epsilon, we have following. We have that, maybe I'll write it here. We have the expectation of the integral of psi n minus f, which is less than or equal to 3 times the minimum of gi in script g epsilon plus the square root of 8 logarithm of 2n epsilon squared over n, and so that's just 3 epsilon plus square root of 8 ln of 2n epsilon squared. Right? So this whole skeleton argument and gives us this, because even if f is outside my my scalable set g epsilon, it will be at most epsilon away from the best g. So this basically becomes the art. Okay, so I mean later on when we get into arithmetic, what I've been doing is kind of completely really out there. I've been trying to keep the trees that I use to construct the histogram such that the trees are amenable to what are called set-valued operations, like contractor programs and all sorts of things. So I can feed this tree that my histogram outputs, and I can start doing operations on those trees directly for control robotics problems, for example, like what the French Navy uses. Or I'll explain what this is. This is again a huge branch of this library that I don't know, earned a lot of money and time, but I myself have not gone back into it. Anyway, I'll explain how this is related. So in fact, that when you limit the scope, the skeletons, and in fact, we work with lattices, so we have an upper bound and lower bound for function, and then the really applied problems are, so you can Brest, northern France, that's one of their naval posts. They have these robots, the French guys do little games in the English channel. So this is so the robots have a boat on the top. It's a sailboat robot, so it uses wind, and then it has a companion, which is a submarine robot. Right, and it's battery powered. It comes up to the top, and they, I don't know, they have some relationship. So, they sort of, I don't know, this is exactly what France wants to use it for, but Chinese have the same, right? China, I don't know anything about the Chinese technology, but they have very sophisticated denial of access games they play, right, in South China Sea. So they can turn loose these, I don't know how much you know, they can turn loose these unmanned objects that can move on their own in a coordinated way in the ocean in South China Sea, and US aircraft carriers can just enter their own risk, which is pretty amazing if you think about it, right? It's a very low tech but incredibly sophisticated solution. So it's the intelligent minefield, basically. But these guys, I don't know what they do, but the main point is the sensors that these uses. So this is a controlled ODE. It's also a decision problem. So what is this thing? It has to fail in some direction. It will get instructions to do something, and then it will have sensors that measure the wind velocity and where the rudder is and all this stuff. And these are set value measurements, so they cannot assume it's a Gaussian distribution centered somewhere. It's all pure set valued operations. So for them to decide how much pulse to inject in this electromotor so that the rudder goes this way and that way, they all have to be interval operations. So that's basically a very natural place. A lot of set arithmetic operations were developed, and the trees I use are actually stolen from that world, except they only map Boolean values to their trees. They use trees to represent subsets of a space, but you can map real or whatever values, and then you can get these. So I guess here the point is, depending on your application, you're not just interested in the scalable estimates just because you have control over this first term epsilon, but you may also have other constraints like set operation constraints, where you may have to sacrifice some of this because your control theory kicks ass and you can shoot the guy. I mean, this is a real problem. So there are trade-offs in what you really want, but here we're just mostly doing some math. So. Okay, so then that's so let's have a little remark. So here epsilon should be greater than 0 such that n epsilon is greater than 50. So let's make a remark. So regardless of how quickly n sub epsilon approaches infinity, as epsilon goes to 0, right? That has to happen. We can choose n epsilon to depend on n itself, right? Epsilon n to be infimum over all epsilon such that the logarithm of n epsilon is less than or equal to root n. So by doing this, so that the expected L1 error of even the psi n converges to 0. Uniformly, provided F is in F tilde and F tilde is clearly bound.
So this would in general just say if you have any parametric family of densities, and you take some compact subset of parameters. I mean, any realistic parametric family that exists, and you take a compact subset, then this would include.
That's right. So.
Or a bounded subset.
Yeah, bounded subset. Well, you can make that as large as you want, and minus n. Yeah. So now let's look at situation 3.
Just one. this remark. Is it obvious that this is true? Because you state that we can choose such an epsilon here, but is it obvious? I don't.
Well, I'm just saying, because I have my, I have this other term I need to worry about, right? In my main theorem, right? So that term basically tells me, what log of an epsilon should be, because.
So just, I think the question is I think you might overcomplicate it. So if you look at, as long as you can take epsilon to 0 at any rate, then the thing on top will tend to 0, right?
Yeah.
And the right-hand side, you have the n. So n will as n tends to infinity, it drags this down. So as long as this n epsilon is finite for every epsilon, then you can just, you can take epsilon smaller at some. As long as the n compensates, it might be very, very, very slowly, but as long as it's always finite, then you can do this at some rate.
Okay.
Yeah, sorry. That's what I was trying to say, but maybe just too much into the right side. Yeah, so it's that's exactly
Feel free to tell me to shut up if I.
No. Please, interrupt. Right? I haven't talked to anyone about all of this since. Basically, I haven't really. It's like mostly in my head, right?
Yeah.
So.
The tricky thing here is the total boundedness is not a weak assumption. So the fact that this n epsilon is finite, this isn't a strong assumption.
Okay. So what if this situation happens? What if f is not in my set? Right? And f is really in my collection of, the set of all L densities, where density is, right? The set of all. So it's not in my totally bounded class, set of all L1 densities. Basically, set of all densities. This is definitely realistic. If you don't want to make any assumptions, then by corollary 10, what we have is the expectation of the integral of n minus f is less than or equal to 3 times the minimum, right? Plus and this is just 3 times the min of g in f tilde, where I have my g minus f, and I add another 3 epsilon, because I've changed the class, plus 8 ln of 2 in epsilon squared. Okay. So, in that sense, the minimum distance estimate is robust. What I mean by robust is it accounts for the distance. It's honest, okay, between the true f and the best estimate in the class f tilde we're looking into, right?
Sorry, what happened in the second final inequality?
What did I do? I mean, this is just by definition of an epsilon and
Oh. Yes. F. No, I read F. So okay, no.
So what is basically, there's no magic here. It's just honest. If F is not in my totally bounded set, it's okay. It will actually account for it. You know. So in that sense, so of course, if F is, this means if F is close to F tilde, then we are okay. I mean, in the sense that you know, this term will not be too bad. So in a lot of our implementation, what we've been doing is, because we wanted to restrict our representations of the densities using these trees to be conducive to all these set contraction and all these set programs, we are very limited. We can only do these axis parallel trees. But what we then do is try to really play with, play with my G epsilons. And I have these G epsilons driven by the data itself. So the data decides how my G epsilons will be formed, and then I don't know, some Markov chain justifications for it, at least asymptotic justifications for the way G epsilon grows as a function of n, and then you know, if the underlying density is continuous and non-negative, so it can have 0 values in places, then I can still make some arguments. I can say the class on which my Markov chain runs to construct my G epsilons are dense enough in the space of continuous functions, and these kinds of arguments you can make. Okay, so it's not hopeless. Even if F is not in some finite skeleton, you can control and asymptotically justify. So again, for a financial transaction problem, what is now a real world example here is, you know, it may be that you know, you say you assume, say, F is continuous, or F has some Lipschitz constant and continuity assumptions, so I can somehow approximate it using smooth class. But then it could be that the true F may live outside this, you know, this continuous density that says strictly bounded from 0, because it could be that in a financial transaction situation, a lot of the Swiss transactions happen at certain times of day. There's almost 0 events in some times, or when you look at certain spectrum of Swiss transactions, a lot of people trade like 10 crowns. They don't usually trade 1, or it'll be in some strange denominations, and there'll be very large holds that have never been in the past, for example. So these kinds of, you know, having 0 support regions inside the density is a very common problem, and often a lot of the classical methods don't do very well there, because they will usually assume the underlying density is continuous and, you know, usually smoother than that and strictly positive.
Does this take account for, if I can have a look at the applications and be very concrete, if you like, and this have taking into account the situation where F is slowly changing or rapidly changing? So I mean, if you take the concrete example, consumer change their behaviors.
Right. I mean, that's okay. That's like even more complicated than this, right? So we're, well, okay. You can Well, maybe. So often you can look at a time varying f itself as some very high dimensional IID where the time is sucked in as one of the coordinates. But we also have to worry,
feature
right?
space would need to have a bit time very dependent as well, because the feature set could be one today, but a completely different one tomorrow.
Yeah, I mean, so maybe Tilo has something to say first. I'll
So just, I think you have. I mean, I think you have to reformulate the question a bit to make, because the thing is, if you just store all past history and everything, then you just build a new estimator for every time point, and then this theory still works. So you need to add some additional restriction to make this. So to make this updating thing a problem, you need to add some additional restrictions to the estimator, because otherwise you just build a new estimator every millisecond, which in practice, of course,
and I see what you're saying, but at the same time, I think this could really be a problem in practice.
Yes, absolutely. It's just, I mean, in order to say whether this theory covers it, one has to say what are these restrictions that we add. For example, saying that the estimator can only depend on the previous estimate and the new estimate, or something like this, and then study this theory. But then you need something different, or at least build something new on top of it.
I mean, but I know what the industry guys do for anomaly detection, because you cannot change, especially in cybercrime, things change very fast. So what they do is basically they'll build a density estimate for, I don't know, a month or whatever, or some subset of the data for that phenomena up to some finite time. And then when things change and new attack patterns begin, they will update that, right? So you are still building a IID density estimate, but then your sampling strategy will, be over a shorter time period, and it will focus only on the things you believe are, giving rise to the density, right? So you can customize all this.
But then you have the risk of your sample set being perhaps too small.
Yeah, that's these are balanced. Yeah, exactly. Yeah.
So that's also a very good reason why you want actual bounds for small n and not just asymptotic theory, for example, because even if you spend a long time on something, you might not actually have sort of more and more data because the underlying world changes.
Yeah, so this is also, that's right. The finite n, because this is not asymptotic, right? This is for any n. This holds. So, okay, so let's look at yeah, so that's situation 3. I think there's situation 4, right? So now f is in L1, and we want to construct some our data. A set of densities. A sub n such that 3 times the minimum goes to 0, and 4 times the supremum of A and script A goes to 0. Okay. So that's the general problem. So to be able to do this, what we started doing is, or what one generally wants to do is want data adaptive strategies. For constructing this set. Okay? This sequence, right? So f and I, and then you have to justify these strategies 1 less than or equal to I less than or equal to kn. Okay. So that's how you can control this side, and then you want this justification to be asymptotic, so as long as n gets large enough, this is going to hold. That is at least the minimal condition you want on this data adaptive FN construction strategies, right? And then on this side, we want better bounds. For this, then that's based on just the cardinality of it. Okay, so there may be other special features you could potentially exploit and come up with something smaller than slice of it. So this basically is the main focus here for theorem 11. So this is the Vapnik-Chervonenkis. They did this when they were working in Bell Labs in the US, in New Jersey. Do you know the history?
I have no idea.
I think they're Russians, right? They sound like Russian. I really don't have to look it up. Yeah, I think so. Vapnik, you know who told me about Vapnik? I think it must be Krajinovic. I don't know. Yeah, someone told me about Vapnik.
So I only know Vapnik from VC and from not having proved a certain theorem that I once resolved. A statement.
There's coffee.
Oh, more coffee.
We're past speaker time, maybe.
Double coffee.
Yeah, we'll have VC theory after coffee.
Should we take a break now?
Yeah, isn't that what we do normally? Yeah, it is. Okay, so I think I'll just have enough time to do some MRS stuff a little bit, maybe.
Okay.
What happened to your thoughts?
I think that's it.
Good, I didn't have any luck.
Yeah, thanks, Steve, for suggesting I do a normal lecture in this sequence. This is good.
It's like cleaning your hands at the end of it.
Yeah.
Yeah. I've now fiddled with the various weird fast XML files for a couple of weeks.
Yeah.
It's surprisingly, I mean, it's fairly straightforward, which is nice. I mean, I'm not saying it's easy or anything, but if you've seen a bit of these types of things, then this is fairly, it's a natural thing to do.
Yes, as I was telling you yesterday, I mean, it's like 20 years since I did any analysis at all. So the beginning of the day was a bit hard getting the steam up, if you like.
Yeah.
Now at least I can see it and I can follow what you're doing, and I can have some sort of idea what's happening.
Yeah.
And that, of course, it needs to be. I need to look at it.
Yeah, if you look at it once slowly, you should basically get it.
I think, but it's also one of these things that much of this looks a bit ad hoc somehow, but once one has seen sort of multiple similar things, one just know these terms tend to appear in these things.
Yes, because you see the similarities in the different lemmas and the
Yeah,
different
exactly.
inequalities. And
Yeah, exactly.
that's cool.
Yeah, what we don't have for density estimation, well, this theory we have only for single machines.
Okay.
So that means it's